So it's my great pleasure to introduce Professor Sanaz Mostaghim, who is a full professor of computer science and chair of computational intelligence and founder and head of the Swarm Lab at the Faculty of Computer Science and Otto von, excuse the pronunciation, Guericke University in Magdeburg, and you can correct that. So just a simple guy from the US. So she holds a PhD degree in electrical engineering from the University of Paderborn, Germany, and was a postdoc at ETH Zurich in Switzerland. And we're very lucky to have Sanaz sharing her work with us today. I've had the fortune of being able to go to the Dagstuhl computer science retreats. And one of the things I look forward to most is actually learning from and hanging out with Sanaz during these periods. She's a fun person to hang out with, great with conversation, and some of the things that she's doing technically is really amazing. A few of recent honors. So if I'm not mistaken, she is the Distinguished Lecturer for IEEE, which is an extremely large honor. And just looking here, has many roles within Germany in terms of leadership roles, and is vice president of the IEEE Computational Intelligence Society and an associate editor of IEEE Transactions on AI. And I could go on and on with accolades, but I want to leave time for presentation. So with that, thank you very much for sharing your time with the Ezra Roundtable in Systems Engineering.
Thank you so much. Also, thanks for introduction. Let me share my screen with you here. Can you see my screen now?
Yes.
Okay, great. So this is Otto von Guericke. This is this guy who invented actually the vacuum. So what he did was he put two halves of the hemisphere together and put 8 horses one side, the other 8 horses the other side, and pulled out the air between the two hemispheres. And he showed the power of vacuum. And vacuum has been used now everywhere in, well, many engineering systems. And he was the mayor of this city, and that's why our university is called after Otto von Guericke. Okay, so that was just a little introduction about the name of the university. So in this talk, I want to give you an overview about my research topic in the area of collective and individual decision-making in time-critical scenarios. I will focus on autonomous systems. And I will right away go to the outline. What you will hear is, first of all, a motivation, why decision-making is so difficult, and what features do I mean with decision-making. Then I want to talk about individual decision-making. At some point, I will turn to collective decision-making. And actually, I'll show you 4 applications. And then I want to talk about how many decision makers can learn to solve multi-objective problems. I will tell you why is it that important and where we are in terms of the technology of today. And the last part of my talk, even is only 1 slide, but I think if someone is talking about decision-making, has to also talk about the ethics behind that, even if I'm not an expert in this area. But I at least want to say that it's an important topic that we all have to deal with. So now let me go on to the motivation and some facts about multi-criteria decision-making and what do I mean with the decision-making in my talk. Basically, I talk about multi-criteria decision-making, and well, the decision-making is not a new topic. Basically, it's very old. There is a very nice work here where they go back to King Solomon about the decision-making and many years ago where people were dealing with decision-making. What I do talk about is decision-making defined by Wilfredo Pareto. And I think many of us know what Pareto dominance is and Pareto optimality is. Decision-making means, in my definition, select one out of many alternatives. So what does that mean? Mathematically says that we have a space here, the search space, where we have our decision variables. Here you see only 3, but we could have many of them. And these are the alternatives that we have. And each of these alternatives here can be evaluated in terms of several functions. Let's say function 1, 2 to m. We call them objectives. And without loss of generality, I will minimize all of them during my talk. And so we can map them in this so-called objective space, where we evaluate basically our alternatives from the decision variable space in the objective space. The optimal alternatives, if we minimize both of these functions here, F1 and F2, they're probably located here. And we use this Pareto dominance, where a solution here, located here, is better than any other solution which is located in this area, because at least it's better than any one in terms of one function or the other or both. Okay, this, I think everyone here knows that definition, so I don't want to spend much time on that. So what facts do we have? If we select one of these red points that I showed you, it means that we will lose the others. So in a way, it means that if we are confronted with decision making, it means we are also confronted with the fact that we will lose many alternatives. It's not actually a pleasant situation when we are in that situation. So, and then what happens also, the decision now can have consequences in future. Imagine multi-steps problems. And decision-making requires time. And why I'm emphasizing on that, because later I will tell you why in time-critical missions, it's very important to consider the time. And why do we need time to make a decision? Because we need to have a knowledge transfer. We need to look at the options, evaluate them, and so on. And so we, can I hear a music? I just...
Hey, Pete, can you mute?
Oh, okay, I thought I'm doing something wrong, I'm sorry.
No, I'm sorry.
Okay, so given all these alternatives, there are two aspects that I want to raise here. From one side, having several alternatives is good. It gives us a sort of confidence when we are making a decision. It's good to have many alternatives, because then we know what we are selecting is, you can compare them with the other alternatives, and it's actually psychologically good to have many alternatives. But from the other side, having too many alternatives is also not so good. And there is a law, which is called Higgs law, that says that increasing the number of choices will increase the decision time logarithm. So all these things produce a lot of difficulties for human decision makers, the way that we all know as human beings. Also, what we suppose when we are making a decision, when we have alternatives, we suppose that they are all optimal. In reality, what happens is that we have to find first these optimal solutions, and that's why optimization algorithms are important aspects at this point. So talking about optimization, what challenges do we have in optimization? There are several challenges, and I want to show you what challenges I am working on in my research group. First of all, large-scale multi-objective optimization. What does that mean? It means that this search space here is not only 3 dimensions, but we are talking about a number 100 to 5,000 variables. So we are talking really a lot of variables that you can have. Actually, we have a recent work that has got good amount of citations where we work on these large-scale optimization problems. Another challenge concerns the objective space, where you can have many objectives. Also in this area, we have been working a lot in the past. What can we do to have to replace the Pareto dominance with some ranking approaches and so on? So that's not that easy when you use meta-heuristics in this area. The other research area, which is also very interesting and is also one of the trends at the moment in the research area, is multimodal multi-objective optimization. That means that, for example, 2, 3, in this case, 3 solutions from the search space map to one solution in the objective space. And many of the algorithms that we have, they actually remove the replicates here. So that's why you have to go and work actually in operations. Your algorithms have to work in the search space. And given that the search spaces are 5,000 to 10,000 dimensions, it's not that easy to deal with this sort of multimodality in multi-objective optimization. Other aspects, I just go through them fast because I see I don't have much time, but other aspects are expensive function evaluations, dynamic problems for problems. You can see here, here's an optimal solution at time t at some point, and at time t plus k is somewhere else. So to detect the changes and to follow the changes is a complex task, and that happens a lot when you have technical and autonomous systems. Robust multi-objective optimization, and at the end, measuring the quality of solutions. These are all the challenges that we have just to find the optimal alternatives. After we find the optimal alternatives, we come to the decision-making process. And the decision-making has also several aspects. For example, finding the optimal, so this is the first one that I said, just finding them is a challenge. Then defining a decision policy. You can set your preferences before the optimization or after the optimization. The time to make a decision, usually we talk about in autonomous system, we talk about a few milliseconds, where you can have in non-critical applications, you can have a few hours or even days to make a decision. That makes a difference if you do not have much time. So you have to come up with some semi-optimal decision at some point. The number of alternatives, as I said, the Higgs law, too many are not good. And then if you had only one, it's not satisfactory. And the last aspect in the multi-criteria decision-making concerns these topics, for example, how you represent the solutions to make a decision, number of consequence decisions, if it is a one-step or multi-step decision. For example, if you have a chain of decisions, can you learn from your past actions? Or then the other aspect is that how many decision makers you have. If you have experienced ones versus non-experienced, if you have a human versus a machine. And the other aspect is that what is the environment of decision making? If you have static environments, so this decision that you make now is similar to the decision that you make in future because the environment is exactly the same, or the same alternative set, the same situation, but changing the environment might lead to different decisions in future. So now these are all, that was a very quick wrap up on what I mean with decision-making, multi-criteria decision-making, and so on. And now when we come to autonomous systems and autonomous decision-making, I mean that fully autonomous systems which are during a mission. So for example, a robot which is flying, I'm talking about such systems. What changes? We have a limited time. The predefined policies, they don't work. So you cannot define the policies or learn them a priori. You need to find the alternatives on the fly. That's why we have to rely on methodologies, which are called a posteriori methodologies, that you find a set of alternatives and the system has to decide on the fly or choose one of them on the fly. Then we have a chain of consecutive decisions. So if a robot is driving or autonomous driving car is driving, you have to make decisions at each time step. Then you have dynamic and unknown environment. You don't know what other cars are coming along. You don't know how the situation is changing, if you have a traffic on the motorway, if the navigation system is working, and all the other aspects in the environment. And you usually can have many decision makers. If you have many robots or many, let's say, self-driving cars, they can actually exchange information with each other. So we probably can use that to have better decisions, and you will see at some point in my talk. So let me go a little bit into the detail, and let's take an example. This example I take during my talk, and I want to show you what do we have, what kind of features do we have here, and I want to go a little bit into the algorithmic part of that. Imagine that we have a robot or a machine, that is a time t at this time here, and it has 8 actions to take from. So you see that each direction is one action. It can go to one of these directions. Here, I'm not optimizing at all. I'm just evaluating what is the outcome here. And what we do have is the distance to the point of interest. It's a very simple thought example here, or a toy example, let's call it. And also the damage. This is an obstacle here, and I don't want to go to the distance to the damage. So this I don't want to have. So I don't want to go towards the damage, let's say, or I don't want to have a collision. So imagine that time t, the robot was here, t plus 1 here, and t plus 2 here. And you can see what happens here. I call them these sort of, so you can see here what kind of situations we have. In the first time step, what we have something which I call a multimodal multi-objective optimization, which I actually told you before. Here you can see that several, for example, 4 and 2, they lead to the same objective value here. In the next time step, you can see that we have, in this case, let's say we have too many alternatives. So here it's selecting 5, 4, 3, 2, and 1 would be challenging. You need to have a better, probably, I mean, if we would have had selected 2, it would be different, or 4, it could lead to different outcomes. So you should have here a good decision policy for selecting one of them. And the question is if you could reduce from 5 to only 2 options. And in the next time step, we have only 2 optimal alternatives. 1 or 2 are the optimal alternatives that you take. And here, the question is what kind of decision policy we should have. If we would have had taken 2, we probably would ended up here. And in time 1, we are ending up here. So it has probably consequences in future, which one we take. One thing I want to draw your attention is that the shape of the Pareto front is changing. So we have some sort of dynamic multi-objective optimization problem. So now let's go through each of these options that we have here. And I will tell you, will show you some methodologies how can we deal with these problems, and what are the research, well, let's say the new research in these areas when you have these sort of problems. Before that, I want to show you how fast everything is changing. And what you can see here, the same problem, a point of interest, and minimize the damage. You can see here the Pareto front. We are minimizing both. And you can see here how this agent is moving. And you can see the agent is moving towards the red point, has to avoid the obstacles. And you can see here in this picture, let it run, you can see here how this robot is moving and how fast we have to select one of these optimal solutions. So this is what actually is happening in the brain of this agent. And you can see the shape of the Pareto front is changing sometimes from convex to non-convex and so on. So about the multimodality, I already told you several solutions from the search space or decision variable space. They map to one solution in the objective space. And you can see here an example. This is a little bit different than the example that we had before, but more or less the 2 routes have one, route 1 and route 5, they map to the exact one solution. So the point is, in most of the existing algorithms, and I was talking to the group in Cornell today, and I saw that you also use a lot the algorithm which is called NSGA2 or NSGA3. And the point is, most of these approaches that we have, they operate in the objective space. It means that if you have duplicates in the objective space, they are removed. But actually, these solutions are totally different in the decision variable space. You can see here, for example, route 1 and route 5, they are not so close to each other. So it means that we need to have operations that are done in the decision variable space. And there have been some works, actually 2008, the first work came out, but they were not really done for large scale problems. And one thing they do is that they change the crowding distance approach that we have from that famous approach, NSGA2. I think you might know that. And that can lead to very slow convergence that we can actually not have in such scenarios. And one thing, for example, we were doing, and actually we are spending a lot of time in measuring the similarities of the solutions in the decision variable space than in the objective space, is that you can, for example, change the crowding distance approach, make a weighted sum approach here in the decision variable space, and then basically the crowding distance that you can measure to distinguish between the solutions, you can not only use, so you can use both the values from the objective space, which in this case would be 0, but then you can have also the portion in the decision variable space, but the distances are far from each other because root 1 and root 5 are different from each other. So you can basically use that as a crowding distance approach and put it in the optimization, and the optimization will then try to keep root 1 and root 5. There are also a lot of other approaches that you can do here. As I said, we are working currently a lot on this multimodality and see if we can find good solutions for such problems. The other aspect that I want to draw your attention is the number of alternatives. And as I already said, the more alternative we have, it is taking also much time for the decision maker to make a decision. So imagine we have these optimal solutions. And now one thing we could do is we could distinguish between these non-dominated solutions and then say, okay, why should we go for the solution F? Or why should we go for solution E or A? We could actually try to compare them with each other. And this is basically what we do is we do not do clustering, because clustering will lose some information that we have, but we are interested to find so-called knee points. A knee point is, for example, solution A, which is actually located exactly at the knee area on the Pareto frontier, or solution G, B, and you could also think about the two extreme points E and D to keep them and to have the knowledge about the extremes of the Pareto frontier. Now the question is, how can we identify these solutions? And one way is that, one good way is that we change the domination criteria that we have to something which is called cone domination, which we basically worked on in 2017 and changed it, made it for a large number of objectives and not only for 2. What is happening in this cone domination is relatively simple. One thing you do is, I have actually a picture here. I show it first in the picture and then I explain what I write here in cone domination. You remember I showed you this and I said this solution, the red solution here, is better than any solution located in this area shown by these 2 lines. And now one thing we do is that we transform F1 and F2 so to another using this omega function, but basically instead of comparing the F1 and F2 values for the domination, we compare the omega and omega 1 and omega 2 in this case for the solutions, and this is basically using the transformation. In other words, what you do basically is nothing else than, instead of having the domination, which were these 2 lines, this horizontal and vertical line with angle of, let's say, 90 degrees, we open that in with an angle of phi. And this is basically what is happening here. So you basically try, the solution A is now dominating this dashed area. It means if you had a solution which was located somewhere here, is now being dominated by A. It was not being dominated before, but now by opening the phi, it will dominate it. So if you put it actually in your algorithm and you keep the optimization as it was before, what that will lead to basically find the knee points like the point G or point A and E and D. And we have done that actually for application in a UAV control center with Airbus in Spain. What we did was we had a problem with 7 objective functions, not only 2. And these are the functions that we had. And you can see here a picture only with 2 of them. And we used also several, we used the NSGA approach with different angles. So the values, the numbers here, 120, 135, and 150, shows how much we open the angle of this cone domination. And one thing I could show you here is now the problem with different number of objectives. Let's say if you would have had 7 objectives, solving the algorithm would deliver 199, almost 200 optimal solutions. 200 optimal solutions for a UAV control center, which is operated by a very simple operator, is basically too much. And by using this sort of cone domination with an angle of 120, 135, and 150, we were able to identify the cone solution, the knee solutions or knee point solutions, and we could basically reduce the number of alternatives from 200 to 7.8, or let's say 7, 3, and 2 solutions. Now the question is, how can we define this angle? This is actually a very good question. This is actually one of the works. We just published it on Archive, and it will hopefully be submitted to a journal. We really hope that it gets well accepted. And we basically try to define the angles in an adaptive way. And in this way, we can see how many alternatives we want, and we deliver to the decision maker the amount that it wants in an adaptive way. And the other aspect that I wanted to talk, that was the decision policy. That was the point 3, decision policy. And here you can see what I want to show you is basically the perfect behavior of this agent. You can see here it's really moving in a very good way. Now I stop this and try to change the weights that I use for the decision policy. Now what happens is, if you change the decision policy, which are used as weights here, you can see the behavior of the agent has changed. Now change it again to other values, and you can see that the behavior of the agent changes again. So basically what I did was, I was giving here a decision policy, which was a set of weights. And in this video, I tried to change them from a very conservative behavior to a very, let's say, risky behavior. And the question is, can we learn that? So I was just playing with these values in this software, and this is what I'm interested in my research, if I can learn the decision policy. The first one, it would be, I work on evolutionary algorithms, so I like to use evolutionary algorithms. So we said, okay, let's learn that. And what you can see here, we run evolutionary algorithms, and you see now, for example, the generation 10, and each of these agents is one behavior in this generation number 10. Or now generation number 20, we have changed the obstacles to be dynamic to make the problem more difficult. And you can see after 50 generations, we are almost, almost not all behaviors are good, but some behaviors are really turning to be close to optimal. And you can see generation 100 here, that one behavior is actually is the winning behavior that we could find. It means that you can use optimization algorithms and learning algorithms to learn the decision policy. The only difficulty, well, there are many difficulties, but one of them is that we cannot explain the evolved decision policy at all. This is done over evolutionary algorithms. Even if you use deep neural networks, that would be the same problem. The other one is the computation time. So the computation time here, it took like a few, I think, hours to evolve that behavior. And if you recall, I told you we only have a few milliseconds. Explainability of decision policy is very important, because when you make a decision, you really need to trace back that decision. And we were working a lot on this traceability. There was also a work that we published last year, where we tried to understand if we evolve a behavior if we can trace it back. And this is some results that I want to show you. We basically, one thing we did was we looked at the first iteration, and these are the qualities of our, let's say, policies or individuals that we have. Of course, the positive, the more positive, the better it is. So, and we have now individual 1 to individual 20. You can see these as colors here. So individual 1 is blue and individual 20 is gray. So you can see here in this picture, in generation 1, they're all present in our population. And then we trace that over the learning, and we see how much impact each individual has in the entire evolution and learning. And we also have something which is called mutation. So this dark blue is a portion that is added. So they are not inherently from the first generation. So one thing we realized that actually in learning the perfect decision, only 4 individuals were important. The rest of them, we could actually forget them. So you can also see here in the color, the orange, the green, blue, and the dark blue one, the semi-dark blue one, they were the ones that they survived to the last iteration. Of course, we have here also the sum of the mutation, but the rest of them, they disappeared. And this is actually a nice research direction that I'm actually following at the moment to see how can we trace the learning of a decision policy. And still it is taking a lot of time to learn the decision if you want to use these algorithms. And this is actually one of the challenges that we have in robotics and in time critical missions. Because if you, it's like the situation I show you here with the cat and the mouse. So we do not have much time to make a decision. We have this limited time of 40 milliseconds. This happens, for example, in computer games or in robotics. And you have basically in such scenarios, you have also a chain of decisions to make, the same as the cat and the mouse. Both of them basically, in order to have a successful mission, both of them, from their point of views, you have to be perfect in every step of this, let's say, mission that they have. And the challenge is, even if you learn the decision policy using evolutionary algorithms or whatever, a pre-planned or pre-learned policy is not efficient. And one example I want to show to you is traveling salesman problem that we used with our agents. And so imagine that we have these points, 0, 1, 2 to 0.9. This picture shows the exact optimal solution if you want to have the shortest path. So you want to go through all these points using the traveling salesman problem solver. And now if you add some dynamics or some, let's say here, physical constraints to the system so that the agent cannot really move in a zigzag way, which is not happening in robotic systems, you can see that the agent is not having a perfect behavior and movement, and it requires a time of 1040 time steps. Now, if we go for a non-optimal behavior, so a behavior that the agent is deciding at each time, at each point, the agent is deciding what to do next and not getting a pre-plan, you can see that it's much faster. It almost changed the time to half. So it means not planning ahead is good, but then if we have a plan, if we want to do that, we only have really a few milliseconds to come up with some solution, even if it probably is not the exact optimal behavior. And for that, we developed this approach, which is called Monte-Carlo, multi-objective Monte-Carlo tree search. Pat, I was talking to you today morning on this approach. Basically, what is happening is that we mix reinforcement learning MCTS plus multi-criteria decision making. What happens is that On the picture on the left, what you see is the typical MTCS. So what MCTS, what you see is that we go for a greedy approach. We have also some upper confidence term here. I think you might be familiar with that. But once we have the multi-objective version of that, then there is not one action that is optimal, similar as in typical MCTS. But we have here, for example, 3 actions that are optimal. And now we have to, first of all, see which actions are non-dominated. We have to measure their quality. And then we have to see which one we take. And if we go for action 1, action 2, or action 3, if we have a balance in terms of exploration and exploitation, and all the aspects that are there. I don't want to go into the details of the equations, and we don't actually have the time for that. But I just wanted to say that if you're familiar with the hypervolume measurement, it can be used at this stage, and you can actually perform the search for multi-objective Monte-Carlo tree search. And one thing I want to show you here is that we have here different, but this is a result of a game where we have 3 objectives to optimize at the same time. We have the preferences, the weights that the agent is taking. And in the last case is the one that actually the agent is learning and is changing its preferences over time and on the fly. And we see that in all our test cases and different maps with different difficulties, this behavior of changing policy and learning the policy on the fly is actually giving us, in terms of all the objectives, the best behavior. This also showed us, when we look at the agents here and their behaviors, it showed us that we have various decision policies. So it means that, imagine here, this combination 3, 2, 3, 1, 2, 2, another agent might have another sequence. And you could have actually a huge amount of various decision policies. And it brings me to the idea that is actually nothing new, these human-like behaviors in machines, where it was proposed in 1986 by Breitenberg, where he was talking about fear and aggression in machines, where you have sensors connected to their motors. And he was saying, okay, the way that you connect the sensors to the motors, it gives different behaviors to them. It's similar to the way we do actually the decision policies. And we also did that in my physics base, as actually also with the real robotic systems. I do it faster here in my part of my talk, because I want to go faster and show you some collective behaviors. But here you can see 2 behaviors. Here we have a very short, let's say, gap. So the agent here has fear because this is too small gap, and it might have some collisions. So the green point here in front of the agent shows how the agent is thinking. So this agent is having a fearful behavior because we have given that vector to that decision policy to that agent, and is not going, even the point of interest is here, the green point, that agent is not going through this very narrow gate. Where in the aggression one, the agent went directly to that point. Now we can let this agent learn this behavior, and that's what I do here in this video. You can see this agent has to take 2 points of interest. One point of interest is behind this wall with this dangerous, let's say, narrow gap. So the agent moves there, has a certain decision policy, sees that there is, let's say, some dangerous situation for it, changes its mind. So it means it changes its behavior, and goes, grabs this point, which is easier for it to grab it. And now I change the view of the simulation, and it goes back again to the same situation and exactly the same situation, but now it has changed its decision policy and goes and grabs the point of interest. Actually, this is, we also try that on real robotic system. I'm not going to take much time here because I want to show you also some results on collective decision making. That's why I will also skip the next slides where I talk about varying complexity of problems over time. These are actually really nice works that we were working on, this distance minimization problem, where the problem, not only the problem changes over time, but also the problem complexity changes over time. If someone is interested, I can talk about that after my talk. But now let's go to the collective decision making. And here I brought you 4 examples, and what I would do is that I will talk about the first example and the last one, and the 2 in the middle I will skip to keep the time, and then I still have another part of my talk. That's why it might be better in this way. So the first aspect is that you remember that I was talking about the point of interest and the wall in between. Now imagine that we have a collective pathfinding. It means that you not only have one agent that has a point of interest, but you have many of them. And let's put it in this way, that one agent starts here. I mean, like this sort of complex behavior. So, and we tell them they have to maximize distance to other obstacles. So like collision should be avoided, minimize the collision. And the other one is distance to the goal should be the shortest path. So they have to go up. Obviously, they cannot go over this wall. So they have to go sort of in a curve and not directly. They cannot go the way that I have shown it here. So one thing we could do is that we could actually, basically you have to find the optimal trajectory for them. And this is not actually a new, let's say, work. But what we do is that we do a multi-objective optimization on that. And here you can see that we have here collision, this distance to the goal for all of them. And here we have the collisions. And these are the optimal set of strategies that they can have. And now I will show you 3 of these strategies, how that could look like. And this one on the left is the one that they avoid collisions. And you can see here the curves. For example, the green one is doing extra curve here, movement to avoid collisions. And you can see it's very sophisticated movement. The one in the middle is some middle behavior, and the one on the right-hand side, you can see that they are quite aggressive in terms of behavior, very close to each other, also close to the behaviors. And in this way, basically, we can model that from the top and give them these trajectories. We also consider sort of vehicle models in robotics. And you can find really sophisticated behaviors. Here is a video, actually, I can show you. This is one of the interesting, it's called circle swap example. It's very complicated, as you can see, because there are different, so you have to consider all the obstacles and also all the other robots, and you have to consider the time in between. You can see actually there is almost no collision among them. The other example that I'm skipping is how would it be if they didn't know where the point of interest is and they have to look for the point of interest. And you can also add dynamics of the environment, and that is very difficult. For example, if you have wind coming or a waterfront coming, so they basically cannot reach the point of interest. I will skip that. But one thing we found out is that one of the optimal behaviors, depending on the communication topology, is that if they want to go against the vector field, they do a zigzag movement, which they learned in a collective way. And actually, if you sail and you are a sailor, you know if you go against the wind, you should go a zigzag movement. And it's exactly what the collective behavior has found in this case. The other example I also want to go, actually I don't have time to go through that, but this is like how you can, if the point of interest is not a point but a contour, how can you search for that? And this is an application where we had to find oil spill on the ocean or fire in the forest. How can you find, and it's very, very difficult geometrical problem if you have non-convex parts of the shape. And you can also use collective behaviors. And here, for example, this picture is very complex because you have really non-convex, so that you don't have the convex hull in the way that we could have. So now let me come to the collective perception. This is the example actually I wanted to show you. This is also one of the examples that is very, that's one of the hot topics in the research area. So you have an environment that has two colors, black or white. And the distribution of black and white is not known to the robotic system. So you have a robotic system, you see these robots, they are moving, they can only observe their own color at their own position. And every time they meet, they exchange the information they have with each other. And the goal is that they should say at the end, which color is the majority in the environment? Is it black or is it white? And one thing we found out, so that there are lots of approaches that you can use. Every time they meet, they do a voting, they try to convince their neighbors. You can use also some sort of Bayesian hypothesis testing and all the statistical approaches that you could use to try to estimate that majority of the colors. And one thing we found out, which is very interesting, is we could actually influence the decision-making by changing the environment. And one thing we found out is if we have very the tasks that the task difficulty is well, very high. In this case, for example, we have 48%, 52%. So 48% black, 52 white is actually very difficult, even for a human being, to estimate that. And you can see here in this example, the white is the majority, and the color of the robots shows what they think it is. And most of them think that this is black. And what we have done is we were thinking how we can make it better, because this is actually not good that they are doing a mistake. And one thing we did was we changed the environment. So basically we used some sort of isomorphic transformations. So by changing the environment of this robotic system, we are able to control them, and actually they are faster in making their decisions. And you can see in a few seconds now they solved it, where in the other case they couldn't. Yeah, so let me go faster. I didn't expect that it might take so much time. I'm sorry. Pat, I think I still have 5 minutes.
Sure.
Yeah. Okay. So then the next topic I want to talk about is that how can many decision makers learn to solve problems, so conflicted problems that we had. And we call it collective multi-objective learning. And imagine you have an environment and you have many robots. And the goal is that they have to go through this gate. Every time they go through the gate, they receive a reward. And every time they have a collision, they get a negative reward. And if they go through this gate exactly at this point that they get a positive reward, they have also more collisions with the others, so they have a negative reward. So it's a very complicated task. And one thing we did was, we said, okay, we are not going to give them the controller, they have to learn it themselves. So everyone starts with an empty controller. So an empty controller is basically, they have no state, and then they try to evolve their states. Like one controller might look like this, so they evolve that maybe they have one state coming like move state, and after some time they mutate that and they might get a new transition to a new state, and over time they can mutate that and get more states, more transitions, they can change their values, they can change their states. So this is called evolutionary robotic approach. And what is interesting is that every time that they meet, they exchange their controllers. So we did that. This is a very old work, actually. It's more than 10 years old work, which I replicated in 2018 and 20. But one thing which we realized was that they were a collective learning approach was much better than a human being. So what a human being would do is that the human being would design a butterfly form of movement. And what the robots have done is they evolve the behavior in that collective way, where they go to the wall and they try to move along the wall. We call it wall following behavior. In this way, they can all avoid collisions and they can go from one room to the other. And the state machine looks, well, like this. This is the best state machine that we had. The gray parts are not reachable. So if you look at these, the black parts, actually they are not, that's not so sophisticated in a way that we could have for this butterfly movement. So you can see how the behavior is. It's actually very nice behavior. And you can see also one or two lost. So this one is lost and these two are also lost. But this is happening a lot if you have a collective behavior. Not everyone is evolving to the perfect behavior. We replicated this work and we changed that finite state machines to hidden Markov models. And you can see here the behavior is a little bit different because we wanted to analyze the brain complexity of our agents. And so we analyzed that and we realized that there are various behaviors. So there is not only one behavior that we have, which is wall following, but also there are some of them who stopped here at this point to help the others to achieve this sort of wall following behavior. And actually, we looked at something which is called integrated information theory, where we try to analyze the brain complexity of those models. And making well, the story short, we realized that the majority of the individuals, what they don't do is they do not look at the inputs from the outside. They just move with the collective. And that was very interesting for us because we knew this behavior from animals. And just to show you some of the works that we have done, that's also actually a colleague from the United States who actually moved to Germany, Ian Cousin. He's very famous. He works on animal behaviors. And he actually observed the same thing with the fish. He observed that he had some sort of fish where he trained them to go either to, basically you can see here on the left-hand side is faster to explain it. So basically he trained the group A to go through the stripe, group B to go to the color, and then he let them in that environment where there was a third arm, which was a mixture of stripe and color. And he realized that half of the swarm goes to the consensus. So they do not look at their training. They do not look at the input. They just follow the swarm. And that happens also in our case. We also analyzed their behavior and we realized also with a multi-criteria decision-making approach. And we realized that half of them, they go towards the consensus arm, similar to basically what we have in our collective decision-making. So I was very fast, but I just want to talk a little bit about ethics in AI and decision-making. I talked about decision-making, and you all know this trolley problem, which is a thought experiment. And now what are the implications for us who work on decision-making, collective decision-making, and all these aspects in this area? Well, if we replace the human with the machine, then many things might happen. Like who is responsible for the consequences of a wrong decision? If it is me, who is the algorithm designer, the programmer, the producer, all these aspects, maybe this is the not so relevant to me in terms of algorithm designer, but more from the law perspective. But what is more relevant for us is that how can we design our algorithms with ethical norms? And for that, maybe we really need to have test problems, or evaluation metrics to see if our algorithms comply with the ethical norms, and also the discrimination, fairness, and all these aspects where they are not part of my research at the moment that should actually be in this area, and we are actually initiating some research in this direction. So now let me come to the conclusion. I think decision making is a challenge, not only for human beings, but also for machines. And I believe that we can optimize the functionality of this autonomous system by giving them the ability to make decisions at runtime. And they can even help us to solve complex problems. I showed you this example with this gate passing. And I have seen in my research that we can actually evolve to various behaviors, and we cannot predict these behaviors. This is definitely something that we have to do research more, and of course the ethical issues must be addressed. At the end, I want to thank you for listening to my talk, and also thanks to my team. Have actually a very nice team of people working with me in the robotic lab, flying robots, and also going to different competitions where we show our robotic applications. Thank you so much.
Thank you, Sanaz.
I'm sorry it took long.
No worries. So, and if folks have to go, we understand, but if you'd like to stay or if you have some questions, do you use the hand, Al? Or I'm looking at video too, or you can just unmute and ask a question. And while folks are formulating a question, I'm trying to figure out. I have a question for you, Sanaz. Where do you see the biggest breakthroughs coming over the next couple of years in terms of autonomy and sort of swarm intelligence?
Well, swarm intelligence itself is in also swarm robotics. I think it is still in its very early stage. The problem with that is we are not capable of having one autonomous system, like one autonomous driving car. We are not still having that system. In swarm robotics, we are talking about many autonomous systems. And all the interactions between them and all these aspects. And to my eyes, decision making is one of the challenges in this area. So if we could, and also traceability. So if we make a decision, if a car or an agent is choosing an alternative, I really need to know how it did that. And this could be one of these aspects, but finding the optimal alternatives, all these multi-criteria evolutionary algorithm, optimization algorithms, these are also still challenges for us in optimization area. And to my eyes, also the time critical aspect is one aspect. But one issue is that you can actually use these systems in places where you cannot have human intervention, like in rescue robotics. Very often you see videos of robotic groups where there is a robot and then goes to some complicated situation and cannot open the door, for example. And we all look at these videos and laugh and say, oh, look, the robot is not able to do that. But if you have rescue robotics, you cannot afford having those behaviors. So the robots have to have robust behaviors, have to take actions, even if they are not optimal. And I think using these approaches that we have can help us to use these autonomous systems in places where human being or intervention of human being is not possible. And this is still a challenge. I mean, I see it myself, swarm robotics itself, also in United States, I know some of the colleagues in Harvard, they are pushing forward and a lot on that research area, but we are all still in early stages of our design. And yeah, so we still need some time to do that. You still can use these algorithms to analyze things. For example, you can analyze collective behaviors of people. You can analyze like election systems. There is actually a colleague of mine at ETH in Zurich who analyzes how, for example, people vote for something. And this is similar to this collective perception thing. So you go meet some people, they convince the other one, and so on. And you can actually use these methodology to analyze the systems.
Excellent. Are there questions from the audience?
I have a question. First, I really enjoyed the talk. Thank you so much. That was great. I guess I'm interested, I don't know much about robotics. I've read a little bit about direct policy search in robotics and coming up with rule systems that kind of govern behavior and respond to the environment. And so I guess I was curious about how you parameterize the decision space for these kind of swarms. Are they each time step? It seems like each time step is independent and is a different decision problem, but I guess I'm just curious about how that's formulated and if you've worked with DPS at all.
Yeah, so you could use things like, you could, there are different applications. And one of them is, planning is an important aspect in robotics. And you could use behavior trees, you could use finite state machines, you could use, many various forms of planners in those areas. But one thing you could also do to learn is that use learning classifier systems to learn how to behave, in which state, how to behave in which form. And this is very promising area to have these sort of learnings, learning rules for, and then the question is, if you have a limited size of rules, if a situation happens and you don't exactly have a matching rule to that situation, what you should do. And yeah,
that's really interesting.
Yeah.
So we are at 1:20. I guess I'll do one last question, unless there's one from the audience, just in terms of highlighting that your group goes from algorithm to hardware, right? And so I imagine classes are fun because folks are doing drone experiments and things like that. I guess, do you want to talk a little bit about how you find students are training themselves differently to go from, hypothetical algorithm to real world robotic experiments?
Yeah, so this is actually something very interesting because in, as a professor, you need to have enough publications, let's say, the output. So the theory, the multi-objective theory optimization is the place where we have a lot of publications and a lot of theoretical works because everything works, you put it there. In a robotic laboratory, nothing works and you don't know why. These are the two extremes. And what we have made is in the middle, we have the simulation computer games, where we have the simulation of real robotics. Actually, we use this physics-based simulation. So we are very close to robotics, even if it's not 100%. And we put some context like games, so we give them some time and so makes it more interesting. And actually we have, my research group has I can claim that it has most number of students in the faculty. And the students, they always come to me and say, oh, we didn't know that robotics is so difficult, especially the way we do it, because we work on swarm robotics. They're very simple robots actually built by us. And they say they exactly see the contrast between theory and the robotics. But this is what they appreciate because they go out and they work in companies and they exactly want to know that in theory we can reach many things. And we also, optimization is not only in robotics, you can use the algorithms for other applications. And we do that, but in robotic area, it's totally different world. A paper for EMO, when we write a paper for EMO, is like in 3 months you have everything. A paper for ICRA or IROS, these are the conferences for robotics, we need at least a year. And after some point, the results are not good. So we have to wait another year to run everything again, evaluate everything, and then submit it to the next year. So these are the challenges that we have. Yeah.
Excellent. Well, thank you very much for sharing your exciting research and your evening. And so
My
I
pleasure.
hope you have a great weekend, and thanks everyone for your time and attention.
Thank you
And
so much.
virtual applause. Thank you very much.
Merci. Thank you. Thank you so much. Thank you. Have a nice day and have a nice weekend.
Thank you.